to basically put in the extra reinforcement. Okay. So the engineering decision then hinges on what's appropriate for VSL. Okay. So as companies test this, the courts react. The courts dictate that no, this was wrong, you lose. And so it's one way of handling it. The other way of handling it is perhaps to think, well, what about our politicians? Don't they make decisions that perhaps influence statistical life? Okay. And how might you measure that? If you think about, if they make a decision and people start losing their lives as a result, if they don't change that law, it means that society, through electing these folks, accepts that trade-off. Okay. If everyone's abhorred by it, they'll reverse the law and those lives will be saved in the future. So another way of looking at it is, let's look at it through that side. Well, I've got one example, and this is posted up on the blackboard, in terms of one that was really easy to measure because of the way it was set up. Quite a long time ago in the United States, there was an energy crisis. This is when the prices of oil started skyrocketing, and the Middle East oil was turned off for a while. And so the nation decided that all speed limits in the nation should be 55. Okay. And it turns out, if you go 65 or 70 or 75, you all of a sudden start consuming an awful lot more fuel, not just 10%, but the inefficiencies of cars means you start consuming a whole lot more fuel. So the law was passed by the federal government, 55 across the nation, the state energy. A number of years later, of course, the energy crisis subsided, and people were complaining that no one wants to go 55, it's too slow. So the federal government said, okay, the speed limits in states have always been state jurisdiction, let's turn it back to the states. So they repealed the 55 law and said, all the states, the 50 states, you could decide what to do. And many of them went up to 65. Okay, some of them stayed, so about 40 of them went to 65, and 10 of them stayed at 55. This is sort of important for the measure. Well, of course, at 65, you're going faster. Reaction times have to be faster, more momentum and what have you. You can reasonably expect to have more fatalities as a result of everyone going 10 miles an hour faster. So the nice thing about this, though, is that during the time that this was being measured, cars were getting safer. As governments were putting in more laws, cars were getting safer. So mortality was going down, okay, but mortality was expected to go up as a result of cars going faster. So this was a study done at Princeton University. Basically, they looked at the one factor, cars getting better and mortality going down because they had 10 states where the speed limit hadn't changed. So they could measure that factor of cars getting better in those 10 states. And then what's left over, because people were dying in the other states more frequently, is the effect of the 10 miles an hour worth of additional speed. Okay, so they got a good sense of what was the effect of those 10 miles an hour. Well, they then looked at how much, so why would one do this? Well, one does this because you want people to get to where they're going quicker. Okay, and so that's a value in terms of savings of time. So you need to then estimate, well, in the 40 states that went to 65, what's the time savings and what's the value of that? So use the average wage rate in the United States, and you come up with a number, okay, per year. Okay. Then, from their study, they figured out how many people extra are dying as a result specifically of these 10 miles per hour increase. Okay. And they did the division. And the division came up with a number of 1.54 million. So in other words, for every life that was lost as a result of going faster, the motoring public saved $1.5 million worth of time in terms of going where they were going. The law has not been repealed. Therefore, one might infer that that is not a bad trade-off. So if I'm an engineer standing up in court and I've used $1.5 million, I might refer to the fact that the U.S. Congress has made that sort of societally acceptable in terms of that trade-off. The trick to do, of course, is to get as far above that 1.5 million as possible. Use that as a floor, and then when you're in court defending yourself, you say, wow, U.S. government, 1.5, we as whatever company, 5 million, and therefore hopefully we'll win the day. Okay. Of course, at 5 million, you're going to be spending an awful lot more money when you do these trade-offs to make it more safe. Right? The lower the value of a human life, the less you have to do in terms of making a car or whatever product safe. Okay. And so, you want to stay competitive as well. You can't make it perfectly safe. Okay. So that's sort of the process in terms of values of physical life. And right now, if you use it like $2, $3, $4 million, you're usually pretty safe. Okay. Any questions about that? So all of a sudden, this gentleman here, he's 20 times what he thought he's worth. Don't spend it all at once. Okay. Okay. What I want to do is, so this is basically the Chapter 6 material. Chapter 7, and I want to give you sort of an example and talk a little bit about it. Maybe I'll just bring the slide up. I have 3 lectures left, I think, right? 1 more week. And so I want to talk a little bit about macroeconomics. I want to do it sort of some justice in the sense of giving everyone a sense of how prices are determined in the marketplace. It's a little bit hard to do in 3 lectures. But I want to talk a little bit about sort of risk analysis as well at the same time. So I'm not quite sure where I'm going to make that trade-off. Most of the risk analysis is simply high school algebra applied to engineering economics. So it's very, very straightforward. And the example I want to give you today, indeed, is an example of that. So let me just, I'm going to bring this up just to put it in context. There are 3 types of analyses that we're going to talk about. Okay. First analysis is break-even. Okay. Now, break-even is really simple in the sense that I've got a business model that I want to build, but I have no idea about the values a particular parameter might take on. So, for example, I know everything about building this model, except what are the sales? So sometimes it's very useful to say, well, this value that I don't know, let it equal X. So, for example, let X equal sales. Build your entire model around X, and then solve it for NPV as a function of X equals 0. That X then is the break-even. In other words, if I think sales are going to be greater than that X, it's project's worth done. If not, it's not. Okay. And so a break-even analysis can be used in that respect, or if I've got 2 options, one is more costly than the other but has energy savings, I can do a break-even between the 2 to see when do they cost the same. And then I need to decide, well, how much am I going to use one versus the other to decide which option. Okay. So this is break-even. Now, the other approach is sensitivity. And sensitivity says, and this is more times the case because engineers are usually pretty good at knowing how to estimate, but without perfect certainty. So this is where we're relaxing the assumption of perfect certainty. And let's say I know what my sales are going to be. They're going to be $1 million, but I'm not sure. Let's have a look and see how the model, the business model, works in terms of me being wrong about the sales. Let's see how sensitive the model is in terms of sales. And so if I'm going to say let Y equals percentage error in sales, then what I want to do is in my model, I want to say wherever there's sales, let me multiply it by 1 plus 1, where Y is the percentage error. So if Y is 0, I'm dead on, and that's exactly the analysis in Chapter 4. Now what about when I do that analysis, and again, this is just high school algebra, and I find that if Y is minus 2%, when I solve this, in other words, this project is no longer profitable if I'm greater than 2%. It means that this model is really sensitive to sales. And if I'm wrong by 2%, then this project's not worth doing. Which might mean then that I'm going to do a whole lot more work to tighten up my sales estimate to make sure I'm happy that indeed I'm going to be very, very close to 1. But in the same breath, if I say, well, if Y is 25%, minus 25%, then it's not sensitive. In other words, sales could be 25% less than I think it is, and it's still worth doing. So oftentimes, this is a way of figuring out on things that the engineer is not really 100% sure about. Do I need to do more work? Right? If I have a cost, for example, and if the cost goes up by 1%, my model tells me it's not worth doing, then I better spend some more time on that cost, estimating it. But if it says the cost goes up by 50%, I don't care, well then I'm done. So sometimes it's useful for two things. It tells you how sensitive the model is, and it tells you whether you need to do any more work in terms of tightening up estimates that are very, very sensitive. Okay. So that's what you do. Risk analysis, I'll talk a little bit about more from a theoretical point of view. It's just talking about probability. Okay. So since I'm talking about chapter 6, I want to just sort of share with you a break-even type of question, and I'm just going to go to the board here. And oftentimes what you'll see on a final exam is you do basic analysis with all sorts of information that's given, and then part B or part C might be what if. What if this happened or what if that happened? That's a signal that it's a break-even or a sensitivity analysis, and then you'll sort of revisit the question and try to decide, what's the recommendation to management in terms of what to do. So that's where it's sort of useful. So I want to do a break-even, and I want to do it in the public sector. And this is let's see, what is it? A transportation type problem. Okay. And it goes something like this. We have a part of, Highway 401 that has a lot of accidents. It's sort of in a low valley type area, and basically when certain weather conditions occur, there's lots of fog. So people are driving along at 110 kilometers an hour, and all of a sudden they can't see where they're going because they drive into fog. Okay. And and of course, obviously there's accidents. Okay. And it suggested that perhaps some warning signs and a wider road might reduce the number of accidents. Okay. And so this is the proposal. Basically, to widen the road, okay, so we have more margin for error, there are fewer accidents, and to have some fog detectors or humidity detectors and put up some warning signs well in advance. Okay. And the question then is it worth doing? Well, here there's no, these are no human life loss. And basically, these are just fender benders. Right? So the benefit of this project to the public is the fact that there will be fewer accidents, and therefore there will be fewer costs of fixing up cars, which presumably means either lower insurance rates, or if you don't report to the insurance company, you don't fix it yourself, right? Okay. So lower costs to the public. But the engineer in charge here doesn't really know how many accidents are going to be avoided as a result of this. But he wants to do the analysis anyway. So why don't we start by saying, let X equal the number of accidents avoided. And once we solve for X, then we can sort of decide, well, is it likely to be on one side or the other? Should we do this or not? That's the approach. Okay. Some of the data here. A fender bender costs $6,000. So it's $6,000 per accident. Okay. Now note this is the cost. But remember, the government doesn't pay to fix your car when you're in an accident, right? It's not a government cost. It's a cost that's being avoided by the citizens. Therefore, it's a benefit to society in terms of this government project. Okay. So this is a benefit. So every time you avoid an accident, people have to pay $6,000 less. Let's see. To widen the road costs $225,000 per kilometer. Okay. And let's see. We have signs, okay, and we're going to use 20 years here. So roadway asphalt lasts 20 years. And the signs are going to be $185,000. Okay. And they only last 10 years. Okay. And of course, you usually have operating and maintenance, so O&M, in this case, $8,000. Okay. And we're not told how to do this problem. So if we have a choice, we'll use B minus C. Don't need incremental or anything like that. Okay, and so first thing to do is to say, well, what are the benefits of this project? Well, and I'm going to use an annual approach. So usually in these problems, use an annual approach, so you're converting everything to into UAC. Usually the easiest way to do this. So the benefits, well, if I'm avoiding X accidents per year, the other thing I recommend is when you have variables, define them sort of carefully. Okay, we're talking about accidents, we're talking per year, so that 10 minutes later when you're coming down to the bottom of the problem, you remember what accident was all about. Okay. In this case, accidents avoided per year. Well, if that's the case, the benefit to the public per year is this. Okay. Now what about the cost side of things? Well, the cost side of things looks something like this. And you don't have to draw a cash flow diagram necessarily, but we're looking at something like this. We've got to widen the roadway, and I think that's 3 times 225. Sorry, I forgot to say it's a 3-kilometer road. Okay. So it's a 3-kilometer road. Okay. And then we've got to put some signs in. So these are the signs at 185. Okay. The asphalt will last 20 years, which is our planning period. Okay. And I need to put new signs in after 10. Okay. And I've got operating and maintenance, where at the end of each year, it's going to cost, what, $8,000. So from the government cost point of view, that's what it looks like. So if I want to now use an annual approach, the easiest thing usually to do is to simply do a net present value of that, and then use a given P. If I do that, I'm going to have the cost side of the equation. So I've got $225,000 per kilometer of asphalt. In this case, I've got 3 kilometers. I then, at end of year 0, put up 1 sign. I then, at end of year 0, put up, end of year 10, another sign. Public money here is 7%. Okay. And so what I've done here now is basically taken all of the one-time only capital expenses and come up with their present value. Right. What I want to do now, since I'm using an EUAC approach, is have the equivalent cost at the end of each year for 20. So, A given P, 7% times 20. Okay. And since this is an EUAC, my maintenance, operating and maintenance is, by definition, at the end of each year. Right, so I add. So all I've done is turn these non-periodic costs into a present value, and then turned it into an end-of-year equivalent cost. And I recognize the fact that operating and maintenance happens each year at the end of each year, and therefore it's already where I want it at the end of each year. And I've got cost. And so I've got, just in terms of dollars, 98,061. Now, is it worth doing? Well, I now want to say, and this is the break-even, right? So the point at which we're indifferent, we don't care either way, is the point where benefits equals costs, right? So we're going to basically, so this is a break-even. So basically say, well, let's solve for where the benefits are exactly equal to the cost. Well, I've got wherever here, I've got X, 6,000, equaling 98. 98. And therefore, my break-even number is 16.3, which suggests somewhere around 17 accidents avoided per year. is where this project starts getting interesting. Okay. And so the engineers now will look at this, and based on their experience, they'll say, oh yeah, we did this somewhere else, and there was like 100 accidents avoided a year, or whatever, and decide what to do. Okay. So this is where we started with not knowing what the goal was, and then built the model around that, and then from there figured out what it had to be for it to be worthwhile, and then of course we decide that. Okay. The second part of this would be sensitivity. Okay. Let's say that I don't have this worked out. Okay. Let's say that having done this, the engineers now say, okay, we will avoid 25 accidents. So that is their estimate. Okay. Well, if that's their estimate, then 25 times 6,000 is going to be benefits. So B is going to be 6 times 25. 150? Okay. So we've done the break even. Okay. Project's going ahead. Now they're saying, okay, it's going to be 20. Sorry, 25. The only thing that they're not really certain about is the cost of resurfacing. Right? Because you go to tender, okay, and if the contractors are really hungry, they're out of work, you're going to get a good price. If they're really busy, well, they don't want your work, but they'll take it if they have a premium for it. That's just the game in contracting. And so maybe I want to now say, well, if I'm going to go ahead with this project, how sensitive is this to the actual resurfacing costs? Well, the approach here then would be to say, let Y equal percentage error in asphalt costs. Okay? And so I now have 150 equaling this, okay? But I'm uncertain about the asphalt costs. Why don't I then say, well, if that's my percentage error, the model is going to be affected by an error in the asphalt costs to the tune of multiplying this number. So this is going to be, just multiply that, 775. So if there was zero error, it would cost 775 to widen the Highway 401 in this area. Okay. But we're not sure. So if I do 1 plus y, I now introduce the uncertainty in the construction costs. Okay. And now what I want to do is C is going to equal now 150, right? So C now is a function of y. It is going to equal to B, which is 150. Okay. And I want to now basically solve for the break-even point. Okay. Since I'm doing B minus C, it's equal to 0. Okay. I haven't done that analysis, but I'm going to get a percentage here. It is going to be positive, right? Because at 25 accidents, it's worth doing, right? So if the costs go up, it's going to be less worth doing. And at some point, where that's what I'm going to solve y for, I've got B equals to C. Okay. That then is